Cloud chamber, a great apparatus for visualizing ionizing radiation. There are extremely many types. This one here is a continuous large area diffusion cloud chamber. Actually, everything here on YouTube is a continuous cloud chamber. Things were already pretty lively just now. You will find out why towards the end of the video. Such a cloud chamber utilizes the temperature-dependent saturation of air with alcohol. The warmer it is, the more alcohol the air can hold. It's equivalent to humidity, but with isopropanol instead of water. The plate at the bottom is cooled to -30 degrees C, and then this creates an area that's getting so cold that the air can no longer support the given alcohol content. There is too much alcohol for the air, and it would actually condense as a liquid. This doesn't happen on its own. It requires a condensation nucleus. This nucleus is formed when ionizing radiation passes through the isopropanol. Alcohol ions are produced and they can act as condensation nuclei, allowing excess alcohol to condensate into fine droplets and creating these beautiful impressions. From now on, when I say we see this or that radiation, it should be clear that I'm referring to the vapor trails generated by this or that radiation and not the individual electrons of beta radiation. What do we see here? Very easily we can see these squiggly lines. They look a bit like someone threw a cooked spaghetti against a wall, and let's see what shape emerges. These are low energy beta particles, electrons, constantly ionizing alcohol molecules and then at the same time being deflected since they don't deposit 100% of their energy, flying off with less energy in another direction, and so on and so on. You can see these ionization trails very clearly, which is very important. Ionizing radiation almost never deposits 100% of its energy in one go. It has so much energy that several molecules could be easily ionized by just one particle. Particle radiation has much higher ionization strength, meaning more ion pairs are formed per unit distance traveled by the electron through the gas. This is also why we hardly detect the gamma background. If we do, they are really very straight and thin dashed lines, because there is not much matter for these fast photons to interact with this gas chamber. Here we have radioactive cesium-137, a beta emitter. Primarily, you can see the 174 kiloelectron-volt beta with these curly lines. There are of course straight lines too, because 174 kiloelectron-volts is just the average energies. The electrons can rush through with a maximum of 514 kiloelectron-volts of energy. For sodium-22, a beta plus emitter, we have to go a bit further, since here beta plus particles, positrons or anti-electrons, which are basically antimatter, are emitted. Now, the curly lines somehow look identical to the electrons from cesium-137. Why is that? Well, it is still as light as an electron. It also has the same charge density with just a different sign to it. To recognize the different charges, you would have to apply a magnetic field, because with the same direction of flight, different charges are deflected differently by a homogeneous magnetic field. By the way, this is how the positron was first discovered, with a cloud chamber to which a magnetic field was applied. Why do they now travel further than the electrons? Shouldn't they completely annihilate and emit annihilation radiation, stuff like that? Yes and no. For annihilation to occur, they also have to stay in the electron shell for long enough time to interact with these electrons. However, the positrons from sodium-22 have an average energy of 216 kiloelectron volts and a maximum of 1568 kiloelectron volts. This means they need much more deflections until they are slow enough for annihilation radiation. We don't see the direct annihilation 511 kiloelectron volts here, because, as I said, electromagnetic radiation is already difficult to detect in a cloud chamber, and besides, they would have to be emitted exactly parallel to the bottom of the cloud chamber to leave visible trails behind. Here I filmed some background radiation as I ran to our blue barrel and brought some spicy air. This air contains an increased amount of radon due to the decay series of uranium, all professionally sealed with parafilm. And? Isn't it genius? You can first see the air pressure from the injection and gradually the thick trails generated by alpha radiation. I couldn't resist, and here again. What you can see very well occasionally is this Radon V. Radon 222 is an alpha emitter, and the daughter nucleus polonium 218 is also an alpha emitter. And sometimes they can decay directly after one another and form this V. Of course, it is also possible that the alpha particle is emitted vertically to the bottom of the cloud chamber and then you don't see the V. However, these individual trails can also be formed from polonium-214, which is another decay product present in the air. Polonium-210 is rather unrealistic because lead-210 with its long half-life blocks it from being in the air. You can also see this in the video where I used high voltage and applied it to some uranium ore. But you can also see the increase in beta- radiation. This is because between polonium-218 and polonium-214 there are also still some beta- emitter. For example, lead-214 and bismuth-214. Here we have our radium cannon, which already has its own video. The basic idea here is we have 3.3 kilobecquerels of radium-226 shielded in such a way that the alphas only come out in just one direction. And just like with the radon air, there is a radioactive equilibrium present here, just with radium-226 in front. This means that you can also see a lot of beta radiation from lead and bismuth. I will say goodbye already and thank you for attention. Soon with NCARD and stuff like that. And if you want to watch Radon Air with nice music afterwards, you're welcome to stay longer. A special thanks goes to the Working Group of Analytics and Fundamental Nuclear Chemistry from Dr. Erik Stubb and the Division of Nuclear Chemistry at the University of Cologne, and to my Patreons. With that being said, goodbye!